Assalamualaikum and good day to our lecturer and my fellow classmates. Today I will be presenting our assignment on chapter 1, the electromagnetic model. In this presentation, we will walk through the fundamental building blocks of electromagnetics, which is covering electric charges, field generation, material responses, and how time-varying field ultimately propagate as electromagnetic wave. To kick things off, what is electromagnetics? It is a branch of physics dedicated to studying effects and magnetic phenomena caused by electric charges. Charges exist in two basic forms, positive and negative. A static charge creates an electric field. However, when that charge moves, it forms an electric current, which generates a magnetic field. Furthermore, when a magnetic field changes over time, it induces an electromagnetic force (EMF). This dynamic interaction between time-varying electric and magnetic fields is what we define as electromagnetic field. Moving to slide 3, let's look at the basic nature of electric charges. Charge isn't a standalone field, rather it is an intrinsic property of matter that causes forces when placed in an electromagnetic field. Measured in coulombs, charge in nature is quantized in discrete steps of E. As for basic interaction, like charges repel and opposite charges attract. In classical electrodynamics, we treat charge as effectively massless. To visualize electric fields, we use the concept of electric flux, represented by field lines that originate from positive charges and terminate on negative charges. The electric flux densities measures line concentration. Closer lines indicate a stronger field. Field lines never intersect. Uniform fields are shown as a parallel lines, whereas non-uniform fields either diverge or converge as seen in the dipole diagram here. Next, let's shift to magnetic field. The magnetic field is a region where a moving charge or a current carrying coil experiences a magnetic force. Magnetic field arises from two main sources: permanent magnets, such as iron or nickel, or electric current flowing through coils like solenoid. Every magnet has two distinct poles, north and south, forming continuous closed loops. The total strain is represented by the magnetic flux density, vector B, measured in Tesla T. On this slide, we analyze how magnetic fields interact with material inside a solenoid. Inside an ideal solenoid, the field intensity is given by H. When magnetic when a magnetic core is inserted, the material atom align with the field, adding a magnetization vector M. This yields the equation B, where relative permeability show how significantly the core material boosts the total magnetic flux density. Looking at real-world application, permanent magnets range from standard nickel alloys and ceramic ferrites to high-performance neodymium magnets. A great practical example is an electric guitar pickup. Permanent magnets magnetize the steel string, and when the string vibrates above the wire cord, they induce an alternating voltage that generates the audio signal. To calculate magnetic fields mathematically, we rely on fundamental laws. Was first discovered in 1819, the electric current deflects magnetic needles. Mathematically, the Biot-Savart law allows us to calculate a differential magnetic field from a small current element. Additionally, Ampere's circuitry law states that at the line integral of B around any closed path equal mu naught times the total enclosed current. On this slide, we look at electromagnetic wave propagation. EM waves are generated when an electric dipole undergoes simple harmonic oscillation. This oscillation produces time-varying electric and magnetic fields that are perpendicular to each other and perpendicular to the direction of wave propagation. In a vacuum, these occupied waves travel at the speed of light. Here, we see the continuous electromagnetic spectrum. It spans from long wavelength, low frequency radio wave used in communication, all the way to extremely high frequency X-rays and gamma rays. As wavelength decreases, frequency and photon energy increase dramatically. Notice how narrow the visible light spectrum is compared to the entire range. Zooming into visible light, human eye perceive wavelength between 350 nm and 700 nm. Using Planck's equation, we can determine photon energy across colors. Red light at 700 nm carries about 1.78 eV, while violet light at 350 nm carries a higher energy of 3.55 eV. This clearly demonstrates in the inverse relationship between wavelength and photon energy. In summary, Chapter 1 bridges fundamental charge interaction to copy electromagnetic fields and wave propagation, laying the core theoretical foundation for modern electronics and wireless communication. That wraps up my presentation. Thank you.